Okay, hello everybody. Welcome to the Chapter 3 material. We are, as a result of the strikes, quite a long way behind. I have decided that what I'll do is make available all of the rest of the course notes with the gaps removed, so all of the material written in. The reason that I'm going to do that is because I am going to use these videos to give a much more direct approach to the material that we're looking at. So I'm not going to be writing out every theorem and proof and example, but making sure that you have the conceptual material that you need. So, with that in mind, let's move to a piece of paper. I'm going to put some drawing pins in this with the hope that something magical happens. So those are two drawing pins. Those are going to be what we'll call foci, so as in the plural of focus. And then I'm going to show you how you draw an ellipse. I'm sure lots of you have seen this before, but there is a string, and if I get the string taut like so, and then I just draw round like this, you can see the picture that you end up getting is an ellipse. So this is an ellipse. These are the foci. So focus 1, call that F1. Focus 2, we'll call that F2. And we can draw lines. So to the surface, to the edge of the picture, as so. And because we know that we've used a single string that has a fixed length, in order to get this, we know all these lengths add up to the same amount. Okay, so let's formally write down the equation of an ellipse, given what we have already. We're going to say that there are focal points, F1 and F2, and then the set of points P that lie on the ellipse are going to lie at a fixed distance away from F1 and F2 if you sum those distances together. So if I let this be R and this be 2A minus R, so that length there is 2A, and I let this be 2C, then that is going to give me all the points that satisfy this, where A is fixed, R is not fixed, but 2C is fixed, gives me the equation of an ellipse. So E is the set of points, so this is P, with P minus F1, that distance, plus P minus F2, that distance, is equal to this fixed distance to A. We can do this in Cartesian coordinates, so that's a perfectly good description of the set of points on an ellipse, but we could write it in terms of x and y if we were to fix a coordinate system. So let's do that. So in Cartesian coordinates, so I'll do this in a slightly different way. I will take F1 to be minus C0, f2 to be c0. That does give me my 2c distance there. I'm going to say that the distance to the sum of these distances again is 2a, but I'll write that in a slightly different way of r plus a and r minus a. A minus r. So as you can see, the sum is still 2a. Of course, that puts my origin in the centre here, so the distance to here is c, the distance to here is c. Let's do some trigonometry. If that is my point P and it has coordinates x, y, then this distance is y and this distance is x. And this distance could be, well, whatever it is, but the points, so the triangles of interest here are this one here, which has length AR, height y, and this distance here is going to be c minus x. And we've also got this length, this triangle here, with r plus a. This length is c plus x, and this length is y. And so those are what we're going to use. So this triangle gives me a minus r squared equals y squared plus c minus x squared. This triangle gives me a plus r squared, so that's the hypotenuse there, equals y squared plus c plus x squared. And if that's my equation 2 and that's my equation 1, if you do 2 minus 1, you can see lots of stuff is going to cancel. So you get the y cancels, you've got the x squared is going to cancel, the c squared is going to cancel, there'll be a cross term of 2cx and a cross term of minus 2cx, so when you take the difference you get 4cx, and similarly over here you're just going to get 4ar. So I will just write out the result of doing this calculation. Do feel free to check it. You get 4ar is 4cx. So we can cancel the 4's. We get ar equals cx. Okay, well, let's just go back and insert into one of these equations. So we've got the this equation here, where you've got something in terms of r and x and y. We want to get rid of the r, and we can use this equation to do it. So 1 gives us a squared minus 2ar plus r squared is y squared plus c squared minus 2cx plus x squared. And we notice that this ar and this cx cancel, which is nice. So we can get rid of those. And then we've got a single r here, which we can write in terms of x. So that gives us a squared plus cx over a squared equals y squared plus c squared plus x squared. And so you can rearrange this to get y squared plus x squared into 1 minus c squared over a squared equals c squared, it was a squared minus c squared. Now you can put that over a common denominator of a squared and then divide all through by a squared, and then you'll see that if we let b squared equal a squared minus c squared, which we can do because we know the length a is bigger than the length c, and dividing through by a squared minus c squared, we get y over b all squared plus x over c x over a all squared equals 1. And that's the equation in Cartesian coordinates of the ellipse. All this works almost exactly the same for the hyperbola. I will sketch out roughly what you do, but without going through everything. So for a hyperbola, you take two focal points, f1 and f2, put them a distance 2c apart, and then you just say that the distance from a point to these two, so the difference between those distances should be the same. So if that minus this is some number 2a, then that has to stay constant. Now you can see that if you can convince yourself that if you draw out what you get from such an assertion about the points, that you find that it has this kind of shape. So that's P. The equation here of the hyperbola is equal to this. It's the set of P such that the distance from P to F1 minus the distance from P to F2 is equal to some constant number 2a. And if you do a similar calculation to what we did for the ellipse, you end up getting that x over a squared minus y over b squared is equal to 1, where c squared, which is c is the distance from the origin to either the focus points, then c squared equals a squared plus b squared. Turns out to be true. So if you have an equation like this for a hyperbola, you can work out what the c is through this equation. If you've got, similarly, if you've got an ellipse, you can do the same thing. Parabola is the other type of conic section that you can have. This is where you have not two focal points, but what's called a directrix, which is the Latin female for director, so it's a thing that directs. So this is the L, which is the directrix. And a focal point here, an origin here, similarly a point, so this will be C from the directrix backwards, and C to the focal point. And how do I get a parabola? Well, it'll end up looking like this if I put the following, if I make the following definition. So I want the distance to, and let's do a nice big one here. I want the distance from the focal point to my point on the parabola to be equal to the same as the distance to the directrix. So if this is the point P is equal to xy, that's the origin, so this distance has to be x minus c. This distance is obviously just y. So Pythagoras' theorem will tell me what this length is. It will tell me that, well, it will relate it to these two, but I also know that this length is c plus x. So this is x plus c. So if I write down the Pythagoras' theorem for this, I will get y squared plus x minus c all squared is x plus c all squared. If you rearrange that, you get y squared is, so these, lots of these terms cancel, and you get 4cx. So if I let P equal the distance from the focus to the directrix, so that's just 2c, then I get y squared is 2px. And that's obviously the equation of a parabola.